So we have a table. We know that f of 0 equals 20. And we're looking at closed interval 0 to 6. We're looking to find the approximate value of f of 6. So we know to get to f of 6, we will start with 20. And we will add the integral from 0 to 6 of f prime of x dx. So, looking at that, we have 20 plus, and we're going to use a midpoint Riemann sum to approximate that integral. So 3 subintervals. So we'll have from 0 to 2, from 2 to 4, from 4 to 6. If you prefer the circles, we've done that too. 0 to 2, 2 to 4. Oops, I don't know what happened there. 4 to 6. Okay. So we're finding just essentially our rectangles. So for this first rectangle here, we'll have 2, because 2 minus 0 is 2, times our midpoint y value, which is 3.5, plus this one here, 4 minus 2 is 2, times our midpoint y value is 0.8, plus, I have the last piece, 6 minus 4 is 2, our midpoint y value is 5.8, or height, kind of depending on how you're thinking of these rectangles. So we'll have 20 plus 2 times 3.5 is 7, 2 times 0.8 is 1.6, 2 times 5.8 is 11.6. So 20 plus 7 is 27, plus 1.6 is 28.6, plus 11.6 is 40.2. So then our value for f of 6 is approximately 40.2. For part B, we want to determine whether or not the actual value of 6 could be 70. And initially this is kind of a bizarre one, but let's start with how we can in general describe f of 6. We talked about this before. So f of 6 is 20 plus the integral from 0 to 6 of f prime of x dx. Okay, what else do we know? Well, we know that f prime of x is greater than or equal to 0 and less than or equal to 7 from 0 to 6. So meaning, really if we look here, f of 6 equals 20 plus the integral from 0 to 6 of 7 dx. Only it's not really equals at this point. It's actually less than or equal to. So f of 6 is less than or equal to 20 plus, now if we take the integral, 7x from 0 to 6, so f of 6 is less than or equal to 20 plus, well, 7 times 6 is 42, 7 times 0 is 0. So f of 6 is less than or equal to 20 plus 42, which is 62. Therefore, f of 6 can't equal 70. And then we're all set. Part C. we're evaluating the integral of f double prime of x dx from 2 to 4. Well, let's just start this, just in general, in kind of a theoretical way. So the integral of f double prime is just f single prime, right? So this is going to be f prime of x from 2 to, evaluated from 2 to 4. So this will give us f prime of 4 minus f prime of 2. Well, conveniently we have these values. F prime is right here, x is right here, so f prime of 4 is 1.7. F prime of 2 is 2. So this integral is actually equal to negative 0.3. Part D, we have a limit. The limit as x goes to 0 of, well, all this stuff. First thing, when we have a limit, we should always just evaluate and see if that works. So if we evaluate at 0, or plug in a 0 for every x, we'll get f of 0 minus 20 e to the 0 over 0.5 times f of 0 minus 10. We know f of 0 is 20. 20 e to the 0, well, e to the 0 is 1, so this is 20 minus 20. 0.5, f of 0 was 20, minus 10. So we end up with 20 minus 20, which is 0, over 10 minus 10, which is 0. Not helpful, except we can use L'Hopital's rule now, so we got an indeterminate form. So then, this is all equal to the limit as x goes to 0. I'm going to take the derivative of the top and bottom of this original limit. So we get f prime of x minus 20 e to the x, that doesn't change when you take the derivative, divided by 0.5 f prime of x, and then negative 10 here just goes to 0 when you take the derivative. Now let's plug 0 in again and see if it works. So now we will get f prime of 0 minus 20 e to the 0 over 0.5 times f prime of 0. Well, looking back at our table, f prime of 0 is 4. So we get 4 minus 20 e to the 0, 20 times 1 is just 20, over 0.5 times f prime of 0, which was 4. So we get negative 16 over 2, which is negative 8.